Okay, so like I said, there's a lot of new terms today. We're going to look at things like a scalar, a vector. We're going to properly define distance, position, displacement, and then we're going to look at how to draw proper vector scale diagrams. So lots of new stuff today. So let's start with vectors and scalars. So what are they? So a scalar quantity is something that only has magnitude. For example, 2.5 meters, or a speed of 23 meters per second, a time of 15 seconds. Energy is also a scalar, so 20 joules, right? Watts is a scalar, right? So your light bulb, 60 watts, that's a scalar quantity. So then what's a vector quantity? Well, a vector quantity also has magnitude, but this is important. A vector also has a direction. So for example, instead of saying 2.5 meters, we can say, 2.5 meters north. Okay? If you have a speed of 100 kilometers per hour on the highway, then you can change it to a vector and say it's 100 kilometers per hour south. Okay? Forces also have vectors. We'll talk more about forces later, but forces are measured in newtons, so you can say 15 newtons, but you know it's a vector because it also has a direction, right? 15 newtons south. So that's the difference between a scalar and a vector. And we're going to be working with both of them throughout this entire course. So let's practice. So on our handout, all we're going to do is label these as vectors or scalar. So I'll do the first two with you. So the first one is 50 kilometers per hour. There's no directional properties, so this one is a scalar. Part B, 6 kilometers per hour north. There's our magnitude and our direction. So this one is a vector. Okay, so I'm going to pause there. Try the other parts to this question and let me know. Okay, so moving on, we're going to go over a couple new terms. First is distance. So we use this a lot in English, and it's not too different in physics. We give distance the symbol d. It makes sense. Okay, and distance is simply the total length of a path that you travel. So for example, here we have a diagram down below. Let's say you travel from the school to the library and then all the way back home. So from the school to the library would be 700 meters, and go all the way back home, it's another 1200 meters. So you simply add those two together, you traveled a total distance of 1900 meters. So that's distance. Moving on, position. Okay, now position is where you are relative to some reference point, or where an object is relative to some reference point. Okay, we give it the symbol D as well. However, we put a little arrow above the D. That arrow means this quantity is a vector quantity. So in our previous example, distance, there's no arrow above the D. It's a scalar quantity, and you can see that in my example below. Right? There's no directional component here. However, position is a vector. For example, let's say we make home our reference point, or you can think of it as the origin of a coordinate system. Then you would say school is 500 meters east of home. So here we have both a magnitude and a direction, showing that position is a vector quantity. And for any vector quantity, we put a little arrow above the symbol. Okay. And the last one, today we're doing distance, position, and displacement. So this might be a new term. We don't usually use the word displacement much in the English language, but a displacement is your change in position. Okay, it is also a vector. So the symbol is this. So you'll see D. D is there again. D is in every single one of these. And then we have the arrow above it. And then we put a little triangle. That triangle is the Greek symbol delta, and it means change. So just looking at the symbol here, we have change in position. And we can actually calculate that, right, by looking at your final position, so where you are now, if you've moved somewhere, where you are now, subtract your initial position, where you were before. So looking at an example, okay, let's say you walk directly from school to the mall. Now remember, home is our reference point. Okay, so your final destination is the mall. So that is 1,000 meters west of home. Then we subtract where you were before, so your initial position, which is 500 meters east of home. Okay, now's the tricky thing. With vectors, you can't simply subtract those numbers. You can't simply go, okay, 1,000 minus 500 is 500. Why not? 500 what? East or west? So in this example, we have both east and west. Now, if we just look at the picture, and you say, okay, if you go from the school to the mall, you're traveling west. And you travel west a total of 1,500 meters. So it's pretty simple just to look at the picture and say, yes, you travel 1,500 meters west. But how do we do that mathematically with the formula? And what we do is we are going to have to make sure whatever we're adding or subtracting, that we're adding or subtracting the same direction. It's almost like when you add or subtract in an equation, you can only add or subtract like terms. For example, 5x plus 5y, you can't do it. You can't say 10 what, right? You can't add apples and oranges. Same with directions. So in order for us to easily add or subtract directions, we need to make the direction the same. Now this is where it's a little bit different from algebra. You can't simply make an x a y. But what we can do is we can change east to the opposite direction west. You can't change east to north because north is not opposite of east, but we can do the exact opposite direction and then change the sign from a negative to a positive. Or if it were originally a positive, we can change it to a negative. Doesn't matter. If we take the opposite direction, we take the opposite sign. So once we do that, then we have 1,000 meters west plus 500 meters west. Now we get the answer that we can see by looking at the diagram, 1,500 meters west. Okay, now looking at it, you might want to say, okay, is the difference between distance and displacement simply the fact that one's a scalar and one's a vector quantity? And the answer is no. So let's look at this picture. Let's say you go from the school to the mall, 1,500 meters west, and then back home. So now you're traveling another 1,000 meters east. If you were to look at your displacement from where you are now, which is home, to where you originally started out from, which was the school, your displacement was actually only 500 meters to the west. Right? Displacement does not care how you go from school to home. You can start here, you can go to the library, you can go all the way up here to the top of my PowerPoint, down here, and just go all over the place and then end up at home. It doesn't care the path you take. It only compares where you were before with where you are now. That's different from distance. Distance matters. If you go from the school to the mall, that's 1,500 meters, and then back another 1,000 meters, you've traveled a total of 2,500 meters. That's how far you've actually walked or driven. And that's distance. So I understand that's a little bit complicated. And we'll sort of try to pat it down with some example problems. So let's go back. I'm going to go back to the handout. Go to the next page. And we're going to do an example problem. And we have this same picture here that we were working with. All right. So here's our same picture. And our question is, what is your distance and displacement? So we're going to have to find both. Right? Remember, distance is scalar, and displacement is a vector. If you, so we have three different situations. Let's consider them all separately. So part A, walk from home. Okay, so we're going to start here. To the library. I'm going to go all the way to the library. And then back home. All right? Then back home. Find the distance. So let's do part I. To find the distance, the total distance, we're simply going to add all that we've traveled. So we've traveled 1,200 meters to the library, plus another 1,200 meters to get all the way back home. So that's a total of 2,400 meters. Now the displacement is going to be a little different. So our equation, how we write it, is displacement is change in position, which is a vector. Right? You can either do a full arrow or a half arrow. I usually do half arrows. Is our final position, which is also a vector, minus our initial position, which is also a vector. And now here's the interesting thing. Our final position, we ended up at home. And since home is our reference point, we were at 0 meters. Usually we would put a direction, but we're not east or west from home. We're exactly at home. And our initial position was home as well. So our displacement is actually 0 meters. So try to think of it like this. Our distance traveled is how far we had to walk. Right? And you can feel that. You burn energy as you walk all the way from home to the library and back home. But your displacement is, okay, what has changed since this morning? Let's say you woke up, you went to the library, and you came back home for supper. And it's supper time, and it says, okay, how has my position changed since this morning? The answer is it hasn't. You're in the exact same place you were this morning. So nothing's changed at all. And that's displacement. Okay, I want to check to see if anyone has any questions. So I'm going to pause it there. All right, so moving on to part B. This one says we're going to walk from the school. Let me just use a different color. We're going to walk from the school to home. So we're going to start here at the school. And we're going to go home. And then to the library. School, home, library. So when we do distance, okay, we're just going to add how far we've traveled. So from school to home, we've traveled 500 meters. And then from home to the library, another 1,200. Which is a total of 1,700 meters. That's distance. For part 2, finding the displacement, again, we need to compare final minus initial. It's always going to be final minus initial. Our initial position was at school, which was 500 meters east of home. So that's our initial, so minus 500 meters east of home. And our final position was at the library, which is 1,200 meters east of home. Okay. In this case, both directions are east, so we're free to simply subtract the magnitudes. 1,200 minus 500, which is 700 meters east. And conceptually, that would make sense. If you start here and you finished here, essentially you've moved from here to here. Displacement doesn't care how you moved there. You could have done anything. And all it cares is that you went from here to here, which is a displacement of 700 meters to the east. Okay, so I'm going to give you a minute, let you try C on your own, and we'll see how you do. All right, so question number 3 says a dog practicing for an agility competition leaves her trainer and runs 80 meters due west to pick up a ball. She then carries the ball 27 meters due east and drops it into a bucket. What is the dog's total displacement? So displacement's a vector. This one doesn't have a nice picture, so usually when we're doing physics problems, it's actually great to draw a picture. We don't have to be great artists, though. Okay? That's why I have a ruler. So I'm going to start by drawing the dog runs 80 meters due west. Okay, so if this is north, then she starts by going in this direction. I'm just going to draw that, and I'm going to write 80 meters, not 8, 80 meters west. Then carries the ball 27 meters east. So at this point, I'm going to backtrack and go 27 meters east. Right, so then it asks for the displacement. Now remember, displacement doesn't care the path you've taken. So essentially, displacement only thinks that you went from here, the starting point, to here, the finishing point. That is our displacement. Okay. Now we've moved in both cases, and we can consider a total displacement. So if you move from point A to point B and then point B to point C, we can consider total displacement to simply be the sum of our other displacements. Let's call this 1 and this one 2. So displacement 1 plus displacement 2. So our first displacement was 80 meters west. And our second was 27 meters east. Move this over, I can see you can't see that. So this leads us into a problem. This one's west, this one's east. We can't simply add them. So what I need to do is take the opposite direction, west, and then take the opposite sign. So I'm going to rewrite this as 80 meters west minus 27 meters west. Now I can simply subtract those and you'll get 53 meters west. Okay, so that's one way to think about this problem, right? That your total displacement is the sum of going from here to here and then coming back from there to there. You can also think of it as just, again, your initial and your final. And we can say our displacement is a comparison of positions from where we were, where we are now and where we were before. So if you want to do it this way, well, you'd have to choose an origin. So if you want, we can call this the origin or home or whatever you want to call it. And so our initial position would then be 0 because we're at the origin. Your final position, well, honestly, that you're going to have to do exactly this to figure out what your final position is, right? Your final position would be, well, 80 minus 27. So at this point, you're at 53 meters west of your initial position, which is just 53 meters west. So you get the same answer. That's the great thing about physics is you can solve a problem using different strategies and end up at the same place. Okay, so I'm going to pause there to see if everyone's okay with this. All right, so we're going to talk more about vectors. Now vectors, as you saw in the previous example when I drew it, I actually drew it as an arrow. It makes sense. If a vector has a magnitude and a direction, you can make the length of that arrow its magnitude, and the direction would be the tip that it's pointing in. And so we can draw vectors as simply arrows. Moving on, vector scale diagram can also be very, very helpful. So again, the tip is pointing in the direction of that directional property of your vector. And now I said you can make the length the magnitude. Now to be accurate with the length, you can draw a scale. So for example, if I wanted to say that somebody traveled a distance of 20 meters, let's say north 30 degrees west, that would be our direction. Right? I could create a scale. And I could say, well, on my scale, if I draw, for every 1 centimeter that I draw, that's 4 meters in the real world. And therefore, if something's 20 meters, then I simply need to calculate, okay, how many centimeters then do I need to draw? In this case, 5 times 4 would be 20, so I need to make the length of that arrow 5 centimeters. And this can be very, very helpful, especially when we're adding different vectors together. Right, so in this case, here's an example of what I mean adding different vectors together. Here we have one displacement. First, we travel 700 meters west, then take a break, and then we travel another 500 meters west. This is a simple example. We could do this in our head. We add them together. They're both west. 700 plus 500 is 1200. But if we were to draw it, right, we can create a scale. In this case, a simple scale would be 1 centimeter for every 100 meters. So first we draw an arrow west. So based on, we need to write what direction north is going to be. Just like when you look at any map, there needs to be a symbol saying, okay, where is north in this map? Same thing. So we need to draw that symbol, and we also need to state what our scale is. So since it's to the west, we draw an arrow to the west. And for 700 meters, according to our scale, the length of that arrow should be 7 centimeters. And then we draw another one connecting to it, right? We connect the tip of one arrow to the tail of the next one. And the next one would be 500 meters. Then you can draw a final arrow showing the total displacement. And if you took a ruler and measured the length, it should be 12 centimeters, which then tells you, okay, the total displacement, according to this scale, is 1200 meters. Now this is a very, very, very simple example. However, it can get more tricky if you're not moving in a straight line. If first you went a certain distance north, and then a certain distance east, and then a certain distance north again, and then west and north and south, and right? It can be very, very complicated, but then you can simply connect in a straight line where you started and where you finished and use the ruler to measure it. Okay? We're not going to go into 2 dimensions very often in this course. In fact, almost never. We're going to stick in 1 dimension. When I say 1 dimension, I mean like a straight line would be 1 dimension. 2 dimensions would be left, right, and up and down, and 3 dimensions would be left, right, up, down, and in and out. Okay, we're not going to do that. We're going to stay on a straight line. So let's go back and try some of the examples that we have on our sheet. Our next page. It's like this. We're going to do question 4. And after we do question 4, I'll let you try question 5 on your own to see how you do. Okay, so question 4 says, Fred is going to visit a friend, but he needs to stop at the variety store first. So he walks 200 meters north from his home to the store, and then 600 meters south to his friend's house. So it says sketch a vector diagram. Okay, so we need a couple of things first. We need to show our compass direction. Let's just make up north. And we need a scale. since everything is like in hundreds, kind of makes sense to say, okay, how about 1 centimeter is the same as 100 meters. All right, so we got our compass direction and our scale. First, we're walking 200 meters north. So let's choose a starting point anywhere on the page here. Start. And we're going 200 meters north. So we're going to go up in our north direction. Because it's 200 meters, the length should be 2 centimeters. So this is where my ruler would be helpful. So you're going to go straight up exactly 2 centimeters. Like that. Okay, so that is 200 meters north. Okay, then, again, connecting the tip of one arrow to the tail of the next, we go 600 meters south. South would be down, according to our compass direction, and 600 meters would be 6 centimeters. We're going to go exactly 6 centimeters straight down. All right, so that's 600 meters south. Okay, so we've drawn all that. Those are the displacement vectors, and now the total displacement vector. Okay, we started here, we finished here. So we're just going to draw a straight line connecting start to finish, which is this one here. Okay, now it says, what is Fred's total displacement? Okay, we can calculate it using the equations, or you could take your ruler and notice that it is 4 centimeters long. If it's 4 centimeters according to our scale, that's 400 meters. And we're heading down according to our compass. It's south. So our total displacement then is 400 meters south. Now we could have done that like this. We could have done it using this equation, where total displacement equals the sum of our other two displacements. Okay, in which case we had 200 meters north plus 600 meters south. Okay, but again, can't just add those numbers. One's north and one's south. So I'm going to show you something. We've already shown that if we change the direction, we change the sign. But what happens if I do change this one? So if I have 200 meters north, and then I subtract 600 meters north, I get a negative answer. I get minus 400 meters north. The answer should be 400 meters south. But again, even with our final answer, we can change it. If we take the opposite direction, then we simply take the opposite sign. So negative 400 meters north is the same as positive 400 meters south, which is exactly what we got here. Okay, finally, part C says, what is Fred's total distance? Remember, distance is a scalar quantity, okay? And we care about the path we take, so we just need to add total distance that is traveled. So 200 plus 600, so it's 200. You don't write the direction. Still write units, of course. Units are very important. We don't write the direction, and we just have 800 meters. Okay, and that's that question. Question 5 is very similar to this one. So I'm going to pause, and if you have questions,